Why is our climate changing? Really? What is the chemical mechanism that makes carbon emissions accelerate global warming? It's an incredibly important problem. And of course, we won't solve it in a chemistry class. But the more we understand about it, the better equipped we are to deal with it. And to understand the impact of carbon emissions on our planet, we need to understand molecular orbital theory. I want to start off with this image. This is the same image that we looked at when we talked about valence bond theory. And the good news here is that we are still going to interpret bonding in a similar way, which is that atoms with their own atomic orbitals are going to approach one another, and they're going to form a bond. And that bond is often formed by overlapping the atomic orbitals of each of the species that are making that bond. So this isn't going away. This is part of molecular orbital theory as well. The key with molecular orbital theory is not with hybrid atomic orbitals. We're not actually going to change anything about atomic orbitals of the constituent atoms that are going to form bonds. What we do with molecular orbital theory is we create new molecular orbitals, as the name implies. That's really the key. If the crux of valence bond theory was in hybrid atomic orbitals, then the crux of molecular orbital theory is in creating brand new molecular orbitals out of the original atomic orbitals that the atoms had before they created the bond. That's really the key. And the good news for us is that all of the information we know about atoms, you'll remember our famous energy level diagram that we draw many, many times in this class. The interpretation of this diagram is really no different than the interpretation of a molecular orbital energy diagram, which we haven't seen yet. I'll draw just a few of these orbitals by hand, and I'll remind you of the different things that we focused on when we had discussed these atomic orbitals. We said that electrons could be in any one of them. That's true. We said that any one of these orbitals could hold a total of 2 electrons, a maximum of 2 electrons, and they had to be opposite in spin. That's still true. We also said that if we wanted to fill this diagram with electrons, we would start from the bottom and work our way up from the lower energy orbitals up to the higher energy orbitals. That's still true. We also said that we would fill degenerate orbitals, or orbitals of equal energy, singly before pairing in the highest spin state possible. All of this stuff isn't going to change at all. We also used this diagram to rationalize how much energy it might take to, say, promote an electron from some state here to some higher energy state. And that phenomenon of excitation, where we say an electron goes from some initial place to some final place, and we calculate the energy difference as an amount of energy that this system is able to absorb, that process, that phenomenon, that that way of understanding how matter interacts with light is also something we will conserve. That isn't going to change in molecular orbital theory. In fact, the only thing that we are going to change in molecular orbital theory is where these orbitals are and what they look like. Really, that's it. And the reason why these orbitals should change is not because the atoms are changing, it's because the atoms are bonding to other atoms. And so really the question is, what happens to each of these atomic orbitals as it comes into contact with another atom? So here is an image that actually does an awful lot of work for us in terms of establishing molecular orbital theory. This is an image that answers the question I just posed to you, which is what happens when I take an orbital on one atom and combine it with an orbital on the other atom. So this is different than valence bond theory in that I'm not simply overlapping them. I'm mathematically combining them. And the first of the options that I want to look at is what I would argue is the intuitive one, right? So we're thinking of a simple molecule. We're simply thinking of H2, right? The simplest molecule that a chemist can think of, 2 hydrogen atoms. And we know that a hydrogen atom ground state is that of a 1s. And so if I've got 2 of them, that means I've got 2 1s orbitals. And the question is, what happens when I bring those 2 atoms together? What are the options that I could be left with when I do this? Now, the bottom one here is what we would call the orbital that I would get from the favorable or additive combination of these 2 hydrogen 1s orbitals. We bring them together and they simply add together. There's not much more interpretation that needs to be done there. So this is really just the combination of 2 1s orbitals added together to make a more of an oblong shape, almost literally as though we took 2 pieces of silly putty or Play-Doh and more or less mashed them together. This is an option in terms of what we could get when we add these 2 atomic orbitals together, and it has a name. Now, some of these names are borrowed somewhat from valence bond theory, and this is no exception. Notice we're calling it a sigma orbital. Now, there's some very important distinctions I need to make here. I'm not calling it a sigma bond. I'm calling this new thing a sigma orbital. And it is a sigma molecular orbital. That's really the key here, because I've got one nucleus here, another nucleus over here, and therefore I have a molecule. And just like I had a region of space around an atom that an electron lived, and I called that an atomic orbital, now I have a region of space around a molecule where an electron lives, and I call it a molecular orbital. That's really the key here. It's the generalization of the notion of atomic orbitals to molecules. But we're not done, and there is an elephant in the room, so to speak, if we look at what we have above. What we have above is what could essentially be referred to as the opposite of what we have below. In other words, if what we get here, this sigma 1s orbital, and I call it sigma 1s because it's constructed from 1s orbitals. So sigma meaning that it overlaps or comes together in one place in exactly the same way as we discussed valence bond theory. So it comes together along one axis, and it's built of 1s orbitals. So this is a sigma 1s molecular orbital in exactly an analogous fashion where this was constructed from the additive combination of our 2 1s ingredients. We also have this option, which is what you would get if you subtracted these 2 ingredients. In other words, as these 2 atomic orbitals come together, if the region of space between them where they begin to touch is actually one where you are subtracting the relative amounts of each of those orbitals, then you get a node in the middle. You get them canceling one another. In other words, the orbital goes to 0 between the 2 nuclei in the molecule, and the remaining bits of the orbital hang out on the left and right sides. It isn't an intuitive thing. It isn't an obvious thing. It isn't something that we would obviously expect from combining 2 atomic orbitals. But the fact of the matter is that if I were to consider the options and what I get by combining 2 1s orbitals Fact of the matter is that I get both of these options. These are both viable alternatives. If I call this bottom molecular orbital a sigma 1s orbital, I'm going to call the top a sigma star 1s orbital. And the star is meant to signify the fact that I have a node here, and more specifically, a special kind of molecular orbital, which I will call an antibonding molecular orbital. Now that's an interesting name, antibonding molecular orbital. It's to be contrasted with the one on the bottom, which is of course a bonding molecular orbital. In other words, this molecular orbital describes where the electrons would be if they were in a bond between these two nuclei. Again, we're talking about hydrogen atoms coming together to make H2, so we know that there'd be a total of 2 electrons. And we know that 2 electrons can be placed in an orbital. So this bonding orbital is essentially the region of space that we would expect those 2 electrons to be in. But it's the antibonding orbital that really raises the eyebrows here. What is it that even means? Well, first of all, the name antibonding orbital I think makes sense if we accept the structure of this orbital in the first place. There is a node directly between the 2 nuclei. In other words, electrons are not allowed to be here. This is a literal zero probability surface. Electrons are forbidden from this zone. So the label of antibonding orbital makes a lot of sense in that context. Electrons are almost not able to be shared between these 2 nuclei. So the name makes sense, but its very existence is, I think, for most students, unintuitive and causes a little bit of trouble. I'll give you an analogy though, without going into the detailed mathematical analysis that one would have to do in order to arrive at this result of bringing together 2 1s orbitals and getting these 2 options. It's analogous to something like, say, the quadratic equation. I think you all have some familiarity with the quadratic equation, solving for x and that sort of thing. And if you remember using the quadratic equation, which is not at all something we have to do right now and has really nothing practical to do with this particular example, the one piece I would point your attention to, though, is with the quadratic equation, you'll recall there was always 2 solutions. You always had one that made a lot of sense and was usually the solution to your problem. And then you had a second solution that was, just sort of part of the math. It just fell out in terms of solving that equation. This is not entirely unlike that, in that if I need to combine these 2 ingredients, there are 2 ways to do it, and bringing together 2 orbitals necessarily should create 2 orbitals. I don't have the ability to create or destroy matter, and so if I remember that a 1s orbital in a hydrogen atom has the capacity for 2 electrons, then that means that my total set of 2 1s orbitals here has the capacity for 4 electrons, which means that the resulting combination should also have the capacity for 4 electrons. And that's precisely what I get if and only if I have 2 molecular orbitals, which are in this case a bonding molecular orbital and this rather strange antibonding molecular orbital. So the fact of the matter is that it exists, and it is one of the 2 possibilities that I get from combining these orbitals, and really we should now think about their energetic ordering. I'm indicating it here, and I'm saying that we've got an orbital, a sigma 1s bonding orbital that's low in energy, and a sigma star 1s antibonding orbital that's high in energy. Specifically, the bonding orbital is lower in energy than either of the two 1s atomic orbitals that we started with. This is a crucial point. This is actually the driving force for bonding itself. The proposal here is that the bonding orbital that gets created from the symmetric additive combination of these two 1s orbitals is actually lower in energy. Therefore, the two electrons that would exist in this orbital, one from the first hydrogen, one from the second, would actually be more stable now in their bonded state than they would be otherwise as a set of independent atoms. So putting two electrons in a bonding sigma 1s orbital is a favorable thing. And that's why H2 is generally a more stable configuration than two independent H's. So we're literally defining the driving force for creating a chemical bond. The two electrons that exist in this particular orbital are attracted favorably to each of the nuclei. And by these nuclei coming together, each of their electrons are able to be attracted to their neighbor's nuclei, which is a favorable thing. And so overall, we've created a stable arrangement of particles here. Now, likewise, I don't think it's too difficult to imagine that the anti-bonding version, the sigma star 1s orbital, is comparatively high in energy, right? It's a system where our electrons are literally restricted from going to the interstitial region between these two nuclei. This is an awkward scenario. And any time when we have a node, we generally have a higher energy orbital. Recall the 2p orbital. This was the orbital with a structure that looked like this, that had a nodal plane going straight through the middle. The 2p orbital is, of course, higher in energy than the 2s orbital, but more importantly, higher in energy than the 1s orbital as well, right? So as we add nodes to our orbitals, they become more fragmented and higher in energy. And that's precisely what is happening here. Now, you can mathematically derive this, but the question I think still remains is there any physical evidence? Is there anything I can see with my own eyes that suggests the existence of these very strange entities called antibonding orbitals? Well, I think there is. And so let's walk into a few more detailed examples to shed some light on those. So one of the things we do, and this is a critically important skill for you to have in this class, is we translate this notion of a bonding molecular orbital and an anti-bonding molecular orbital into an energy level diagram. And so here's an example. This energy level diagram is not at all different than the kinds of energy level diagrams we've been looking at before. In fact, if I were to take all of this that I'm highlighting here in pink and remove it from the diagram, then what you're left with is the same old energy level diagrams we've always been dealing with. There's the hydrogen 1s orbital indicated as a box, and I've put an electron in it, and that's about it. I haven't indicated the 2s or the 2p or any of those others, but you get the idea. This is the same sort of notion. Likewise, if I get rid of all of the pink stuff here, we could consider the exact same thing by getting rid of all this on the left, and here is just that same old atomic energy level diagram for the other hydrogen atom with an electron in the opposite spin state. What we do here, though, is we envision what happens as I bring those two elements together. So on the right here is my independent hydrogen atom. On the left is my other independent hydrogen atom. And what's indicated in the middle is the new orbital energy level diagram that I get as the combination of these two atoms. Here I see my bonding sigma 1s orbital, and of course my anti-bonding sigma star 1s orbital. And this is perhaps a more concise way of indicating where our electrons are. So just like with the case of atoms, we would have electron configurations, where for this particular hydrogen atom, my electron configuration is 1s1, a relatively simple case. We can now have both electron configurations and orbital energy level diagrams in exactly the same way, but for molecules. So for example, my H2 molecule now has its own electron configuration, which isn't 1s or 2s or any of those types of orbitals that we've already learned about for atoms, but is instead a sigma 1s2. Same exact idea. Orbital label, and to the exponent is how many electrons are in that particular orbital. So the exact same concept is persistent. In a molecular orbital scenario, we have an electron configuration, and we also have an associated energy level diagram that goes along with that electron configuration. So these are entirely transferable concepts. The only difference is we are now no longer talking about the familiar 1s, 2s, 2p, and so forth. We're talking about a new construction. What do we get when we bring together two atoms? And a common thing that you'll see over the next 10 to 20 minutes or so is that we always get the additive combination, which is favorable and lower in energy and is the result of a constructive addition of each of the two orbitals. And we get a subtractive or destructive or unfavorable high energy combination of those same two orbitals in which a node is created between them. Luckily for us is that even though it's not necessarily an intuitive conclusion that we should get an antibonding orbital, it is at least consistent, and we will always get an antibonding orbital from the combination of any two atomic orbitals that we bring together. So let's go looking for some more evidence, shall we? Let's build up the number of electrons we have here. Even with just the diagram you see on your screen now, if I expand out, we can realize that this diagram can also treat the helium atom dimer. Right? So helium is a 2-electron species. It has the configuration of 1s2, right? So the helium electron configuration is there, 1s2. And here's an example of a helium atom orbital energy level diagram, just like this one over here. And if I bring those two helium atoms together, or more specifically, if I bring together two 1s orbitals, we've already seen that I get a sigma 1s and I get a sigma star 1s, a bonding molecular orbital and an anti-bonding molecular orbital. And there's a really interesting effect that happens here. Because a helium atom has 2 electrons in it, bringing together 2 helium atoms means that my molecular orbital energy level diagram, which is what I'm showing here within the pink box, will contain the grand total of 4 electrons. And just like in all cases of orbitals, as I fill it with electrons, I fill it from low to high, singly before pairing. All the same rules still apply. And so in this case, I fill 2 electrons in the sigma 1s bonding orbital, and then the final 2 electrons in the sigma star 1s bonding orbital. And this is where things get interesting. I've got just as many electrons in an anti-bonding orbital as I have in a bonding orbital. In other words, I've got just as many electrons trying to thwart my attempt at bonding as I do electrons trying to help me bond. The net result here is no bond at all. And this shouldn't be surprising because helium is a noble gas. Helium is an element that is inert. It doesn't react. It doesn't make bonds, not even with itself. The helium dimer does not exist. And molecular orbital theory is giving us a pretty concise explanation for why that is. Obviously, we can look at the helium electron configuration and say, oh, well, you know what, it's 1s2. It won't want to bond. We predict that it would be inert. But that's not necessarily satisfactory because you'll recall in our discussion of valence bond theory, we had the case of beryllium. And beryllium had a configuration of 1s2, 2s2. So you might say the same about beryllium, that it was satisfied, that it didn't have to bond. But it certainly did. So having full orbitals doesn't necessarily guarantee that you will be inert. But if we look at the molecular orbital diagram for helium-2, we can see that there is no stable configuration. That's a really key word for us today, stable. We've got 2 electrons that actually benefit from the arrangement, from bringing these 2 helium atoms together, but we've got 2 electrons that don't benefit at all and are forced into a very high energy antibonding orbital. And the net result is that these electrons are not as stable, not as energetically happy, so to speak, as the independent atoms were. And so we would predict no net bond. Now, there's a phrase that's used in molecular orbital theory called bond order. Now, bond order in molecular orbital theory is essentially an indication of what kind of or what degree of bonding do we have in a particular system. And to calculate bond order, what we do is we go and tally the total number of electrons in bonding orbitals, and we subtract from that the total number of electrons in anti-bonding orbitals. So in this particular case, I can see that I've got 2 electrons in bonding orbitals, and I'll subtract from that the 2 electrons that I have in anti-bonding orbitals, as seen up here. Now, because a bond costs 2 electrons, I will divide this total by 2 so that I can calculate essentially how many bonds I have. But really, that's a meaningless thing to do at this point because I can already see that the numerator of my fraction here is 0, and therefore I predict a 0 bond order. In other words, no bond. Now this can be contrasted with H2 because in H2 I also have 2 electrons in a bonding orbital, as we can see here, but I have no electrons in antibonding orbitals anywhere. Now, if I divide that by 2, because I need 2 electrons in every bond, I discover that I have a bond order of 1. In other words, I have a single bond between these 2 H2 atoms. So we're not using phrases from valence bond theory like sigma bond or pi bond. We are using phrases like sigma orbital. That's really the key. And we substitute the notion of a single or double bond with this notion of bond order. And we can say that H2 has a bond order of 1 and helium-2 has a bond order of 0. In other words, doesn't exist. Now we can continue to play this game on up the periodic table. For example, lithium with a configuration of 1s2, 2s1, as is indicated here on my diagram. If I bring 2 lithium atoms together, I'm indicating one of them here on the right, the other here on the left. Bringing those 2 together creates the molecular orbital energy level diagram that you see in the middle here. So this is what's inside the pink box here. This is the molecular orbital energy level diagram. And the moral of the story here, I suppose, is that we see the exact same result. The bringing together of my 1s orbitals creates a favorable sigma 1s bonding orbital, and it creates an unfavorable sigma star 1s antibonding orbital. Likewise, the same thing happens with my 2s atomic orbitals. As they come together, they create a favorable combination that is a bonding orbital made from 2 2s orbitals coming together, and an antibonding orbital made from the subtractive combination of 2 1s orbitals. So again, our sigma star 2s orbital would look very much like our sigma star 1s orbital, only larger, of course, because we know that the 2s atomic orbitals are large. But this diagram, I think, reminds us of, yet another interesting consequence of molecular orbital theory, which is that it is virtually impossible to pinpoint the electrons in a molecular orbital diagram that are responsible for, say, a particular bond. For example, the Lewis structure, if you will, of two lithium atoms bonding is laughably simple. I really only have one valence electron for each lithium atom, and so I just make a bond between them. And in a Lewis structure, we say very clearly, there are the two electrons right there. That's the bond that is joining these two atoms. But in a molecular orbital energy level diagram, we've got all 6 electrons in there. And while it's really tempting to say that these valence electrons, or the molecular orbital that comes from the valence atomic orbitals, are responsible for the bond, the fact of the matter is that there's 2 electrons down here that are also in bonding orbitals. And to make matters worse, there are 2 electrons here in the middle that are in anti-bonding molecular orbitals. So what is the role that they are playing in the bond between these 2 atoms? It's an interesting question, and it's perhaps an ill-formed question, because really the only thing molecular orbital theory tells us is how to combine the various atomic orbitals from any atoms that you're bringing together to make a new set of orbitals, a brand new set of molecular orbitals that can then, of course, be populated in exactly the same way. It's not actually appropriate to pinpoint a bond per se. It's just a set of 6 electrons distributed in the way that we would expect if they were in a sigma 1s, sigma star 1s, and sigma 2s orbital. It's a little bit more abstract. But we still have the ability to do the same sorts of things. We can talk about bond order. And if I look for electrons that are in bonding orbitals, I see 2 here, and I see 2 here as well. So I have a grand total of 4 electrons in bonding orbitals, and I will subtract from those bonding electrons the 2 anti-bonding electrons that I have, which I can see right here. So that gives me a grand total of 2 net bonding electrons, which if I divide by 2, tells me that I've got a net of 1 bond, right? Or a bond order of 1 in this molecule, which of course is precisely what our Lewis structure was telling us in the first place. But there is so much more detailed qualitative and quantitative information in this molecular orbital energy level diagram. For example, only this molecular orbital theory approach gives us this notion of virtual antibonding orbitals, right? We learn something based on that. For example, I know that the lithium molecule should be able to absorb an amount of energy that corresponds to this difference, shouldn't it? My valence electrons are here in the sigma 2s bonding orbital, and I have an available energy state, or orbital, up here at the sigma star 2s state. So the difference in energy between these two is an amount of energy that this lithium molecule can absorb. This is exactly analogous to our atomic situation where we were creating barcodes, right? Where elements could absorb certain photons or elements could emit only certain photons. Well, that's also exactly true of molecules. There's nothing qualitatively different about that at all. This is the same exact consequence. The only difference is that the orbitals themselves are different. Now we predict that the lithium molecule can absorb a very specific frequency of energy. And likewise, if these electrons were already excited, we can predict what sorts of photons would be emitted from the lithium molecule. And we can go one further than that. Notice that this high energy state is a sigma star 2s orbital. In other words, it's a antibonding molecular orbital. Well, doesn't that mean that if I take an electron out of this sigma 2s and promote it up into this sigma star 2s by virtue of exciting this molecule with, say, a photon, then wouldn't that alter my bond order calculation? Of course it would. I would have one less electron that is bonding, and I would have one more electron that is antibonding. Well, that's really interesting. That makes this 3, and it makes this 3, and it makes this total 0. Wow, it looks like if I were to excite this lithium molecule by providing enough energy to take one of these electrons and put it into this particular energy state, I could, in principle, dissociate this molecule. I could make it fall apart with light. That's fantastically interesting and also fantastically useful. Modern chemical synthesis can actually use lasers of very specific frequency to play with bonds in a chemical system. You can very specifically tune which bonds get broken and which bonds get formed by understanding the physics involved in this exact scenario. It's an incredibly powerful technique. And so not only do we have a diagnostic technique to see what we have, in other words, does this molecule absorb exactly this amount of energy? If so, it looks like it's lithium too. But we also have a method of manipulating the molecular structure itself using light. It's an incredibly useful realization. And this all comes from molecular orbital theory.